which is following. Okay, again in the text, there is a wedge that has an angle theta. There is a mass on the wedge. There is a mass B, so the mass of this one is MB, mass of this one is MA. And again, assuming frictionless surface. All right. And we would like to know the acceleration of mass A and the acceleration of mass B right after I release MB on the surface of MA. Okay? Because it involves the force and acceleration, I'm saying because it involves force and acceleration, the tool, best tool, in other words, we could use is Newton's second law. Of course, we only know one tool. So let's apply Newton's second law. Because it involves forces and acceleration. Okay? I'm emphasizing, okay? The reason why we select Newton's second law to see what's going to happen in this problem is because this problem involves only forces and acceleration. So let's apply Newton's second law on each mass. Okay, for MB, okay, this has to be theta. And I can see that there will be a force acting on normal to this surface. Maybe I denote that is MB because this is mass V. And of course there must be some friction force, but assuming that is 0, because we assume that the surface are frictionless. And also there should be some force due to gravitational force field. That is MBG. No other forces are possible on this problem. And that has to be equal to mass times acceleration, that is MB, some acceleration. Now, you have a freedom of selecting coordinate. And I said how to select a coordinate for your convenience. Which one you feel convenient? That's a big problem. If you are very good in applying Newton's second law, then you can find very easily what would be the y's coordinate to express the acceleration. Okay? If you look at this problem, you can immediately see that there should be some acceleration downward, okay, parallel to the surface of wedge. Okay? And then the wedge, the mass would also experience the acceleration due to the motion of wedge. So I express acceleration by observing carefully the motion of mass B. Or you could just say, oh, I want to use XY coordinate, X and Y. But looks like, I mean, it would work, but using XY coordinate in this case, it's not really incorporating with the physics that we can see. So let's use the acceleration that looks like a very well cooperated physics. So what is this? This is the acceleration of A, and there is a mass, so MBAA. Okay, then what is this acceleration? This acceleration, obviously, acceleration of mass B observed by mass A. Right? So relative acceleration. So this acceleration plus that acceleration is total absolute acceleration. Okay, let me emphasize, very important one at this point. Newton's second law. This acceleration is the acceleration measures the coordinate that has to be absolute coordinate. That means the acceleration that is measured by the coordinate that is fixed on the ground. That makes sense, right? For instance, when you ride a bicycle, okay, and you want to see the motion of yourself on the bicycle, okay, what you do is you have to find out all the forces acting on you, right? And you are measuring the motion with respect to the coordinate that is attached to the ground. Otherwise, if you measure your acceleration with respect to the coordinate attached to your bottom, then the formulation has to be different. We will talk about that problem later on. But up to now, acceleration we are handling is acceleration measured by absolute coordinate. Okay? Therefore, this is quite acceptable. This is total acceleration can be seen on the ground. If you are using so-called moving coordinate attached to the mass MB, what you can see only is A, B, A. All right? And removing this and apply Newton's second law on this graphical expression, then this will induce error. Okay? Everybody got it? This is very important. This is very important highlight of this lecture. And then let's look at wedge. Then what kind of force you can see? According to third law, there I can draw reaction force NB. Of course, frictionless. And also I can see there is a normal force acting on the surface of a wedge, NA. And again, assuming small friction. And also, I can see some mass B, mass A times G, that is the weight of a wedge. And that has to be equal to mass times acceleration, mb, ma, a, and the direction of this acceleration has to be this way, right? You have a question, okay? And also there is a possibility to have another acceleration in this direction, but assuming that, again, the wedge is moving translationally only. This is the end of our graphical expression of Newton's second law. Okay. Then, what if I again apply Newton's second law upon to this two mass system? Okay. Try to see the problem. Okay, here is a mass A, wedge, and here is mass B. And again, he argued that everything between this mass and this mass is internal force. So I don't care about it. And then say there is a normal force. Frictionless will remove this friction force. And there is MBG and there is MAG. That's the force I can see at this. If I see two masses at the same time as a system, and then I say this has to be equal to this will move with the direction of parallel to the surface that I call MAA. Okay, and obviously this will move to that relative to the wedge, so that I call that is the relative acceleration. And also this will move like that, therefore I write like that. And then I said this is 0 in x direction. So I say 0 equal to MB plus MAAA, and I say AA is 0. And I say MBG plus MAG minus NA has to be equal to the component of this one in that direction, so on, so on. So what's the problem to consider two masses as one system and apply Newton's second law? What's wrong with that? Looks like that approach looks simpler than see the problem and separate mass, but does not provide us the same result.